Hi, so I can switch to the slide directly. So, just a few things about my background is that I have a software hardware background without computer science degree, but with an industrial system and electronic degree. So that's just to explain you the perspective I came from. And so this talk will be based on NaxRiscv, which is a project which started 2 years ago, where the idea was to develop a FPGA softcore, RISC-V one, which has a few not so common features for FPGA softcore, like out-of-order execution, out-of-order memory load and store, multiple issues, so multiple instructions each cycle executed, memory coherency, multi-core support, so really a lot of features. The idea was to push that forward and also to experiment with other ways to describe hardware. And so, yeah, this talk will share my experience on that and give you some keywords, so that if one day you are in a situation where you have kind of similar problem, it may help you. So, yeah, sometimes it will take some time to switch the slides because that's only a dual-core softcore running at 200 MHz in Debian, showing the slides. And so it all starts with hardware description. So when I learned hardware design 12 or 13 years ago, it was VHDL, eventually Verilog, but basically the way things were told to me is that there is no alternative to industry standard. But now, with time, things really moved forward a bit. There is a set of open source alternative tools you can use to describe your hardware. And what they often have in common is that they are based on the same paradigm, which is using a general purpose programming language and a software API to explicitly define your hardware. So for instance, there is some in Scala, like Chisel and Spinel HDL. There is some Python-based one, like Midgen, Amaranth HDL. And it can be quite slim and pretty. So it's just to give a simple example. I will not go that deep, but like for instance, to define some simple hardware with input increment, you say, okay, I want input Boolean hardware signal. I want a register named counter, so okay, I want a reg of the uint 8-bit type with a reset value 0. I want a combinatorial signals, which has always this value, and so on. So it gives you the same level of control than VHDL and Verilog in practice. But it can go much further. For instance, like if you have an if statement in your software programming language, like Scala or Python, you could add or not add some hardware in your netlist. If you have a for loop, you may add some hardware multiple times in the netlist, but it can go much further with data structure and algorithms. For instance, you can use software dynamic arrays in a CPU design. In a CPU design, you may have multiple flush interface, and you may want to store all those flush interface into a dynamic array. So, simple example. And then you can go to things which are more evolved, like hashmap. Hashmap can be really useful to elaborate your hardware. So here's an example also applied to CPU design. CPU design, you have multiple stages, like fetch, decode, execute. And basically, you can model the stage as being some hash map between some hardware data type, like program counter as a hardware data type of uint 32 bits. So it makes a relationship between the hard type and the hardware signal in the netlist, which instantiates that hardware type in the given stage. Then you can access those hardware type in the stages that you want. And finally, you can ask some software algorithms to automatically pipeline things between those hash maps. So you can go really deep. And if you are more interested in do that, you can check, for instance, here some documentation, how NaxRiscv was made, how he pushed the ways you can elaborate your hardware. So then you have the instruction set assembly, architecture, sorry. There is a few which are open source, free to use out there. There is OpenRISC, there is more recently RISC-V. And for instance, for RISC-V, I have to say now the toolchain is really usable. It's quite stable. I remember at the beginning there were often breaking challenges between, for instance, Linux and OpenSBI, but now really things work well. And it's maybe still not that easy to buy some RISC-V chips that you can program yourself, but in many ways, many companies are embedded some RISC-V in their silicon to implement some functionalities without even telling us. So it's really quite common. You get also all the toolchain, GCC, LLVM, QEMU, Linux, Debian port, all of those things, which then lead you to designing your CPU. So this is, I will not go that much in depth in it. I will just zoom on some part of it. So that's how NaxRiscv architecture is. You have some fetch, stage, decode, allocate, rename registers, track dependencies, out of order issue queue. Then you have some execution units. And for instance, for the execution unit, there is really two worlds. There is the one which have a fixed latency with really good response time, and the one with variable latency. It's really two worlds apart. And what I will focus on during the next slide is just the branch prediction. Like here you can see, for instance, there is a branch target buffer, there is a G-sharp prediction, a return at rest tag prediction. We kind of named that branch prediction, but that is much more than this. So it doesn't need to be done exactly as I will show you now, but that's to give an example. And this is not even exactly how NaxRiscv does it, but it's quite close. And basically, branch prediction is more about predicting what will be the next program counter that you need to fetch really, really early in the pipeline. So early that you don't even know what instruction you are fetching yet. And so you have to predict a lot of things, like you have to predict if there is a branch or a jump instruction in the bytes that you are still fetching. You have to predict if there is a jump or a branch. You have to predict where those predicted jump and branch would go toward if they are taken. You have then to finally predict for the branch if they should be taken or not. So there is really a lot of branch prediction happening early on, and everything which goes below is only about correcting those branch predictions made really early. For instance, in the decode stage, you know exactly which instruction you are executing, so you may correct a few things. And in the execute stage, it's not really about executing the jump and branch. It's really more, again, being sure that everything went right before with the prediction, else correct the CPU execution path. And it's not shown in the diagram here, but it's also about generating the data, which will allow the CPU to learn how to predict the next instructions, to make the branch prediction learn about the program. And so, next slide, it's loading. Oh yeah, so because we are in an open source design, we can simulate the whole CPU, we can simulate really everything, cycle by cycle in desktop. And this is a graph which shows like which instructions are being executed by the CPU, when the CPU is fetching what instruction, when the instructions are being renamed and decode, when they are waiting the out-of-order dispatch queue that all the dependencies are solved, when the instruction is being executed, and when they are waiting for commit. So this graph is generated using Konata tool, which is also an open source tool. And this specific trace is showing a spectre attack done on the NaxRiscv CPU, where, for instance, we can see here we generate a very long chain of dependencies using some load and store, which work on the same address multiple times to create some load to store hazard, in order to generate a very late branch misprediction that will allow us to execute a lot of badly speculative code, allowing us to attack some memory protected by the MMU, then how to generate some side effects out of it. I took the wrong direction. And it takes a lot of time to load pages. And so, yeah, like, one interesting thing of that is that some people then can really try some attacks and really see the behavior of the CPU out of it. But I also try to imagine that often when I had to program some microcontroller, I had an issue, I had some bugs in my software, I wanted to figure out how to interconnect to the DMA, or for instance, I want to improve the performance of my software. Like having full access of the hardware design and being able to simulate those things can be really helpful. And so then you go about multi-core requirements if you want to run RISC-V Linux. And there is not that many hardware requirements. You just need two things. You need hardware cache coherency, and you need inter-CPU software interrupt. So inter-CPU software interrupt is really trivial, so I will talk about it, but I will really focus on hardware cache coherency. Because with my background, so I already come from a world where I have microcontroller, eventually a really low-end processor, and softcore FPGA often work like this. What they do is software cache coherency, where, for instance, if a CPU wants to write the memory, you will have to flush explicitly with a software instruction its data cache to make it visible to others. And when a CPU wants to read the memory, and he knows that it may have been written by somebody else, he needs also to invalidate explicitly its own data cache before reading it. That's really old school, and some software are less and less compatible with those things, like for instance the RISC-V Linux port. And what you need is hardware cache coherency, loading, yeah. And so that's one example of it. That's just to give some idea of that world. There is many other ways to do. It more or less looks like how Tiling works, not exactly, but it's close. Where basically the idea is that if your CPU data cache wants to do a memory operation, he will have to acquire a copy of the memory block he wants to work on, but also permissions to do operations in it. Like he may ask read-only permission on a given copy of a memory block, or may ask read-write permissions. And here is an example, for instance, same case than before. Assuming all the caches are empty, CPU 0 will want to write the memory, then the data cache needs to acquire the copy and acquire read-write permission, so he do an acquire request to the interconnect. Knowing that no other cache in the system has a copy of that memory block will directly grant the memory block and the permission to CPU 0, and then when CPU 1 wants to read the memory, he asks a read permission with a copy, and then the interconnect will trigger a probe to CPU 0 to ask CPU 0 to go back to downgrade its permission and to provide a clean copy of the memory block back. So the funny thing about that is that you can really observe this kind of memory coherency scheme happening in very modern hardware in very simple ways. For instance, if you run this C code, where you have two threads, one incrementing the first element of the array, the second thread incrementing the second element of the array, you may end up in two very different performance cases. Either the two elements of the array end up in the same memory block and you will have absolutely disgusting performances, because basically between the two CPU data cache, it's ping-ponging the read-write permission and the memory the copy of the memory block all the time. And if it ends up that the two elements of the array are in different memory blocks, there is no interference between the two data cache, and things go 20 times faster. And that's on a 2-year-old desktop CPU. So it's really something which is observable. And so yeah, if you're more interested in do that, you can, for instance, take a look at the Tiling specification. And one thing is, because I had to implement the L2 cache to work with this Tiling specification, it also exposed some performance tricks which are not necessarily that obvious at the first look. So those tricks are not necessarily true for all L2 caches, but for the one which I implemented. To give you some example, the L2 cache will only support one pending transaction per 64-byte block. So if you have two requests on the same memory block at the same time, one will have to wait a quite long time. So it also means that you should avoid to split your memory access into smaller things than 64 bytes if you know you want to read 64 bytes. And for instance, the L2 data cache will only support memory transactions up to 64 bytes. Getting a very long burst for your video DMA to be efficient will not help quite the reverse. So going above 64-byte access may have negative effects. There is a notion that keeping memory burst aligned is really important. Up to a given point, you can have alignment aliasing, which also, I mean, there is a lot of little nuance which can appear with this kind of design, which then lead you, when everything, all of that work, lead you to deploying your SoC with some peripheral inside a FPGA. And I have to say, the FPGA vendors are king when it is about locking customer in by providing easy-to-use tool that they can't use on other FPGA. So there is ways to avoid that. There is some open source tool to design full SoC with peripherals, like for instance LiteX, which is in Python with Median. And it had quite some peripherals like DDR4 and 3 controllers, open source, SD card, Ethernet support, USB host, SATA, PCI, many things. And one interesting aspect of LiteX is that it provides a template, SoC template that you can modify just by using some command line, so really easy to customize your SoC a little bit, and you can deploy it on many different FPGA dev kits already. And for instance, using this command line plus a few modifications to get USB host support and JTAG, you get a full SoC which can run Debian. So that's the SoC which is running now on this board. So one thing is that one peripheral which was kind of really missing was USB support. USB is kind of scary because it's a very big specification. Implementing a Linux driver is something which also scares me. But it gives so many connectivity, like keyboard, mouse, audio, flash drive, SD card, UART, Ethernet, Bluetooth, Wi-Fi. So one interesting thing about USB is that there is also some open source specification about how you could implement a USB host controller inside a SoC, which is, for instance, named OHCI. Maybe you already heard the OHCI keyword. It is the specification of it. And so if you implement this specification, you get a lot of things for free. Like there is already a Linux driver for it. There is already a U-boot driver for it. And there is even a NetBSD driver for it. So I implemented this USB host driver, and something funny happened. Somebody with an old SPARC station running NetBSD ported this USB core in a FPGA, connected it on a very old S-bus, and got USB support on his platform as well. So yeah, if you're interested, there is some documentation about these peripherals there as well. And yeah, synthesis, place, and routes. So at this point, you only have a bunch of Verilog code, maybe VHDL code. So you need to translate it into a bitstream to load into your FPGA. You can use the FPGA vendor tools like Vivado, Quartus, and so on. But there is also some open source tool you can use for that. Not necessarily for all FPGAs, but for quite a few, like for the Xilinx 7, Lattice, ICE40, and SCP5. So the tools like Yosys, NaxPNR. I'm just not the good person to talk about it. I'm not really updated about the status of those tools, but know they exist. So then, I don't remember what is the next one. I have to wait. Oh yeah, running Linux. So yeah, that picture was from somebody, some people which reverse engineered an oscilloscope and made the system run on it, running Linux and Doom on it. And basically, running Linux is scary, and here are the requirements. You need, okay, if you want to run multiple CPU and DMA, you need hardware cache currency. You need machine mode, supervisor mode, user mode, that's a privileged mode like the x86 ring level. Here is the specification, which is really hard to read, so if it's hard to read for you, don't worry, it's not your fault. You need MMU support, not really, but I would say you need it. Atomic support, the same, you need it. not really, but I would say you kind of really need it. And you need SBI. So SBI means supervisor binary interface. It's kind of a BIOS. So it is a software specification of a system call that the supervisor is allowed to do towards the machine mode to get some feature. So while you run Linux, this BIOS is still running. And for instance, Linux can say, okay, please put a serial character on the terminal, or maybe Linux can ask, please set a software interrupt in 10 milliseconds for me. So there is really a bunch of functionalities which are implemented in this machine mode BIOS, which is really still running while Unix run. And you have a specification for it here, and an open source implementation here named OpenSBI. And the funny thing is that it implements enough functionalities that Linux can run without any hardware-specific driver. You will not get a block device driver, but enough to run distribution like build root and so on. Okay, then the even more scary thing is running Debian. I really knew kind of nothing about Debian before trying it, but it's not that bad. Once you get some documentation about it, generating image for Debian is quite simple, and the requirements are the following. Like, you need RISC-V, 64-bit support, with integer, multiply, divide, atomic extension, floating point extension, double point, floating point extension, and compressed instruction set. So, unfortunately, you need a lot of RISC-V extension for that. I was hoping we will get at least a 32-bit version for our FPGA softcore to keep things small, but I lost that hope. I guess it will not happen. So you need a Linux kernel compiled with quite a few additional flags and some storage like SD card for the image itself. And so yeah, if you're interested in do that, there is some documentation here about it and a video to document at what speed you can boot Debian, run Doom, run OpenTTD on it on a dual-core NaxRiscv running at 100 MHz. Then, yeah, I don't remember the next one. Yeah, here all the fun begin with all the package of the world. Like, from embedded hardware engineer, accessing to this kind of software libraries it feels kind of weird. Like when you are used to build root with its limited set of packages, and now you have access to a full Debian desktop environment on an FPGA, yeah, it's something weird. It's not necessarily the most fluent experience you will get, but it runs Doom just fine. Okay, so now it's kind of the reality check. I may have had quite some dark words here, but I will try to communicate to you my pain and suffering during those times. I don't know if you have seen the Breaking Bad last episode, where there is Jesse running away in his car, screaming crazy because he is finally free. That's really how I feel a few times in my life, including the day the SoC was finally working and I had Debian running, everything seemed stable, until something happened, like a bad kernel message. It is really scary. It's really a roller coaster. Because you have to understand this kind of project is years of work, and you only see the light of, you seem so close from the light, and then it ran away. Yeah, too much information for me. And so here is a real example of what happened. I had a dual-core Debian running well for 1 hour, and then I had an RCU freeze. That means that one of the core was freezing. And 1 hour of runtime to get a hardware bug is really scary, because it means it had to wait 360 billion cycles before triggering the bug, while it was running Debian, which is really running a lot of software. I had a lot of software running around in the CPU, and I had to wait that long for the bug to happen. So it's impossible to run it in simulation, because it will be 40 days of simulation waiting for eventually a bug to happen. And so also another very scary thing is that maybe the bug happened 10 minutes ago and by some cascading effect finally shows its symptoms. So you hope you get some clue, You hope it will not take you weeks. You hope you will one day fix it. And in that case, I was kind of lucky. The core was still alive on JTAG. I can still probe its status on OpenSCD. I could see the program counter, which was stuck in the best function for a thread to get stuck in, so the row spin lock, which is already a good thing. It's not in some random function that gets wrong. Really row spin lock. And forcing that lock to unlock using OpenSCD, writing the memories, tracking things around, got the CPU back on track. And yeah, it was just bad bad memory currency made by the CPU data cache. So yeah, it's really the hard part of all of this. Debugging is scary. Once you get a working design, you will not like to modify it at all. You will have a lot of resistance about modifying something which works, especially when you reach SoC, CPU level things. And so I think that is the last slide. It is about simulation. So when I learned hardware design in school, we were obviously on the industry standard tools. We had Model Sim, there is also VCS and this kind of industry tools which will cost you too much money as an individual to get. You may get some free version which are locked down in terms of size, unusable for this kind of big design. And the thing is, there is really open source alternative to those big industry tools like VHDL for VHDL simulation, Icarus Verilog for Verilog ones. Those work great, except for speed. So if you need speed, which is what you need to simulate CPUs, is Verilator. So Verilator is a really important tool in the open source toolchain, I would say, because you can simulate the CPU at this kind of rate on a modern CPU. It's about 100 times faster than what those tools will do. So, and basically what it does, it translates your Verilog into a C++ model that you can then simulate. And also, if you have one day to develop CPU and stuff like this, you need to, running the simulation alone is not enough. You need to run your CPU in a lockstep manner with a reference model to check every cycle what the CPU is doing, to catch the error as soon as possible. That's one of the big mistakes I did for a long time. I didn't have that, but this will save your sanity. And yeah, those connotated traces here, you can easily detect bugs with these lockstep things, but finding performance bug is really hard, and having this kind of traces is not only really interesting, but is also really helpful to find out performance bug. And so that's it. I hope you had a good time. And one thing, so if you have some open source project which brings something in the world which fills a gap, take a look at the NLNet Foundation. They helped me a lot, and they may help you as well. Thank you.
Thank you very much, but the good times are not over yet. You have the possibility to ask a question out there on the internet from Fediverse, also Matrix and IRC. But also here in the room we have 4 microphones, so please queue up behind them, and then we'll take some questions both from the room and also from the internet. So we have the first question on the microphone here in the front to the left.
Hello. Yeah, first of all, thanks for the nice work. And, you know, there has been a lot of problem with working with build root, you know, with getting packages and all. So getting Debian is very good thing. But again, yeah, the 64 port, RISC-V port is only possible, right? So the question I have is that how do you see this project growing in the LiteX ecosystem? Will we have an official Debian port that, so Debian already has a RISC-64 build that gets generated? Is it possible to put it directly on and generate the, let's say the image and root the file system there and directly port it on my FPGA after I built it? I built a bit stream. How do you see that working?
So I was surprised how little modification I had to do on the Debian image itself. It's so simple. I don't think we need anything specific. just providing the README, I think is good enough because it's really trivial. There is nothing specific to the dev board itself I had to do. Nothing specific, all vanilla. Only the Linux kernel had to have the LiteX drivers, but that's Linux side, not Debian side. So I don't think we need a specific Debian port for this.
Okay, so just the bit stream needs to be provided with the 64 port, and Linux kernel has to be built with 64 port.
Yes.
And then I can take a Debian rootfs from the official Debian packages and all.
Yeah, right.
Thanks.
Excellent. We have one more question here, over here from the left.
Hello, thank you very much for the talk. So I have a question about the prefetching and the branch prediction and such. So that can, as you showed, right, it can cause security problems. And so what I've been asking myself is whether it's like feasible or realistic to have a CPU completely without branch prediction and still have it be usable with at least some software, right? Or if it's really, we have to give up on that. And
so, for instance, there is NaxRiscv that you can configure to not have a branch prediction.
Yeah.
And you can run build root just fine. It's not that bad, I would say. You have between, you halve the performance into. At least, and for out-of-order CPU, it's even worse because the pipeline being longer, correcting bad execution take double the cycles. So yes, it is feasible to have a CPU running Linux without branch prediction. You can run Doom on Vex at about 35 frames per second in Linux, so it's not that bad.
All right, so the performance hit is still within the same order of magnitude. Or the performance, you said half?
Between Vex without branch prediction and Nax with everything in, there is about double.
All right, that's really good. That's actually really good. Okay.
Good. We need to use the microphones because otherwise the internet can't hear it. But before that, we have a question over here from the right.
Oh, this one. No, it's not half. It's 3 times. 3 times.
And now the question to the microphone to the right in the room.
Thank you for the talk. So I'm working with the CVA6, and there's a bunch of, depending on which simulator you use, Verilog or Model Sim or whatever, there's different bugs that the actual simulator had. I just wanted to ask if you had any similar experience.
No, I didn't have that for 2 reasons. I only used Verilator because that's the only tool I can access which is fast enough. But also, I would say, I can't prove it, but I'm using SpineHDL, which generates some Verilog code, which is really made to be accepted by all tools. There is no human creativity in the generated Verilog anymore.
Okay, thank you.
Good, and then we have one more question over here from the left.
Yeah, hi. First, thank you. Do you happen to know Boom, the out-of-order CPU developed at Berkeley?
If I know him?
No, do you know the CPU? Is it also possible to use all the peripherals with it? And is it usable compared to NaxRiscv?
So I never tried Boom myself. I will just tell you a bit more, but the Boom documentation was quite useful to get in the out-of-order CPU design. That was great. But I have no experience at all with it. I don't know how easy it is to deploy it. I don't even know if there is a light export of it. I don't know.
I don't know either.
I think yes. I think there is a Boom port on. We'll have to verify.
Yeah.
And then you can use all the peripherals LiteX has if it's done.
Okay, thank you.
We have one question from the internet, and while we wait for the Signal Angel to read that out, please don't hesitate to go behind one of the microphones. If you're in the room and have a question that you want to ask, don't wait until after the talk and go up on the side. Please ask it so that everybody else can hear it and get the benefit of the answer. So Signal Angel from the internet.
The internet is asking itself why the simulation is so slow on the FPGA, especially in a cycle-accurate manner.
The question is why the simulation is so slow in an FPGA?
Yes.
I mean, it's not really a simulation anymore. I mean, okay. So I understand the language. From somebody from my field, FPGA are not simulation devices. They are really something we can deploy in proper industrial device. But for the ASIC people, the FPGA are seen like a simulation platform. And so from that perspective, this FPGA is 13 years old. It's a mid-range FPGA, so yeah, it could run at least 2 to 3 times faster with a modern FPGA high-end one. But I didn't hear the full question. Did I answer the question already, or?
Signal Angel, could you repeat the question?
I'll ask the internet for if they are happy with the answer.
Good. While we wait for an answer from the internet, then we have a question in the room over the microphone left front.
All right, so this is about the lockstep experiment that you did. Do you see some potential there for running 2 cores in lockstep?
It is done. It is done. RVLS, I specifically developed RVLS for that. Mm-hmm. So RVLS is a tool I had to develop because I didn't want to run a simulation of a dual-core system without having everything checked because I know the hell it is. And it does that. And the tricky thing is about handling memory coherency in a lockstep fashion. And so there is some additional communication between the CPU probes and VLS to generate the trace, to feed him with CPU traces, which is like to tell when the load was executed, so he knows the timing at which the global memory ordering should be looked at to know the value to read. There is when the load is committed, I don't remember why, and the store, there is when you commit the store, and when you broadcast, when you have to say when the store value is broadcasted, that means written back into the L1 data cache.
Okay, more specifically, do you see also some opportunity or possibility to run different implementations?
Yes.
In lockstep?
I mean, what do you mean, different CPUs or
different core implementations?
Yeah, it should work out of the box. So the way how RVLS is implemented, there is multiple front end, and basically the front end that are all CPU specific agnostic. And you have one front end where you directly drive RVLS via C calls. So you really have high performance for live checking of the CPU. Or you also have a file front end when you fill command lines which document all the traces, and then you feed that file into RVLS, and it will tell you if it's good or not.
Thank you very much. I think we have our final question on the microphone to the left again.
Yeah, what do you actually use for tracing? Because there's this...
for what?
For tracing. There's this, for example, this simple RISC-V trace, which is meant for implementation in ASICs.
Tracing at runtime.
Yeah.
In hardware.
Yeah.
I use nothing except JTAG with just GDB, OpenSCD. So I have nothing for real tracing where you can extract execution graph, if it's that what you mean.
Yeah.
So no, I have nothing for that. I just have the regular RISC-V specification for JTAG debugging implemented, but nothing else.
Okay, thank you.
And we have some feedback from the internet.
There's another question from the internet. It seems the previous question is answered. The new question is, how is instruction fragmentation in general handled? Especially with new CPUs have vendor-specific optimization.
How the CPU prefetch is done?
Instruction fragmentation in general.
The instruction fragmentation?
Yes.
Yes?
Yes.
I don't understand that. And then the second part was if there was something specific about the FPGA vendor itself, right? I'm trying to understand.
I think this is where your email from before comes in handy. So we'll ask the internet to send you an email with the question, because I think we're out of time. So please give a warm round of applause for the talk.